Okay, welcome back. Not only talking time with caffeine, but welcome back to our mini series Before Earth, as we take a look at what the universe was before a little rock of, of dust decided to come together. But before we get to that, let's get to our guest today. Uh, Introduce yourselves in whatever order you want to introduce yourselves.
Well, I'm next to you, so I'll go. I'm Michael Vandegraff, also known as Dr. Tapioca Weasel. I am an atomic physicist, but we're talking about cosmology and stuff, so that's fantastic.
Yay.
Am I next or?
Sure.
I'll go next. Hi, I go by the name of Ness, and I'm not an expert on physics. I'm more focused on plant biology, but I am eager to learn about the history of the universe that we inhabit.
And I am Landon Knoll, a astronomer and planetary scientist, here to talk about Before Earth number 02. Because if you might recall, Before Earth 0, because a lot of good things origin at 0, was the Big Bang process. And Before Earth 1, we spent about 2 hours talking about the first second of the Big Bang process. And as Dapper Dino kind of pointed out, it might take us a while to reach a point of modern times if we keep going at that rate. In fact, I did a calculation, and it would require us roughly somewhere around 100 trillion years of show to reach present age. Which by the time that happens, there's another, nearly 100 trillion worth of stuff we'd have to keep going. So instead, we've decided to speed it up.
Well, hopefully our descendants will pick up the podcast for us after we're gone.
Absolutely. So we're going to spend probably about of a couple hours talking about the first 100 million years, which a lot of stuff happened in the first 100 million years of the Big Bang process. We've already covered the first second, so we'll start after that.
It's not as jam packed as was before the first. Not as jam packed anymore.
Yeah, but a lot of stuff has happening, and I hope again the idea is that you can get a notion of the amazing history of our cosmology, as well as stuff we know and stuff we don't know, which is a whole bunch of stuff.
And in the previous episode, we talked about going from 0 seconds to 1 second, but now we're going from 1 second to 100 million years.
Yeah. Although technically, we probably started at a Planck time tick, but because it's problematic whether there was a 0 or not. But that was to see that go and watch a BE0 instead.
The 0 point is a hypothetical point where you reach the hypothetical singularity, right? That's where the 0 comes from, originally speaking.
Well, as I say, there's different models of how that happens. Mm-hmm. But as I say, that was covered in there, and so we're going to be starting with the starting at after 1 second.
Real fast. If anybody out there wants to support us in the stream, and you can leave a tip right there in the chat section right there at the top of the chat. If you want to help the channel and help all of us make better content about the universe.
And I also say that if you could consider hitting at some point the like button to support this channel too, that would be appreciated. That little thumbs up can be quite helpful to his channel. So any other things we want to talk about before we dive in to the first second?
I was going to say we probably want to review what the state of the universe is at t=1 second. So I guess that's diving into it.
Well, okay. In that sense, at the universe was much hotter and much denser than it is now, and things were much closer to each other than they are now. The temperature was roughly on the order of 10 billion Kelvin, and energies were in the mega electron volts. The early universe was probably around 10 light years in radius. So that's around 100 trillion kilometers in radius.
Like just enough to reach the most distant neighboring stars, right? Yeah.
Well, actually, there weren't stars then. And
I mean, compared to our the current universe, like the closest stars in our neighborhood is like Proxima Centauri, right? And that is about how many light years is it up?
3
away?
for an fraction. So that's a radius. So the original universe was small. Now it's important to understand, if you remember from when we had the period of cosmic inflation, that the universe went through a rapid expansion, which is why we now have a universe which is 10 light years in radius after only 1 second.
And at this point, we don't even have the atoms yet, correct?
That's correct. But something interesting happens around this time, and that is something called neutrino decoupling. And to understand this lovely graph here and what neutrino coupling is, let's go and look briefly at the standard model. There's a nice chart, I believe. If you advance there. And here, this is the sort of the standard model of particle physics. And you see that there are 3 sort of generations of matter, fermions: electrons, muons, and taus. And they each of those, electron, muon, and tau, have a associated little neutral one, which is the name that I think was Fermi came up with the notion. They were seeing in nuclear reactions where all the energy didn't add up. There was something missing, and people thought, well, there must be some neutral particle. But it turned out that the neutron was discovered around that time, and that neutron was actually fairly massive compared with the slight missing mass. And Pauli came up with a particular solution. He called it a neutral particle, but because there already was a neutron, Fermi suggested in a conversation with Pauli that they call it the little neutral one, or neutrino. So it's a nice Italian word, neutrino. And neutrinos are weird particles. They are in this zoo of particles that come around. They're probably one of the stranger ones. I don't know if anyone going to comment on neutrinos before.
I was going to say neutrinos are like particles, but like they're barely there at all. You know?
Yes.
Yes. Neutrinos, they barely interact with anything. They do occasionally collide with stuff and interact via the weak force, but almost never. A single neutrino has to pass through like a light year worth of solid lead before it has like a chance, actually, a probability of hitting.
I did the calculation. It's around 3,000 light years of lead, and so 3,000 light years is roughly 3,000 times, or basically 30 trillion kilometers of lead, solid lead. You'd have a 50-50 chance of a neutrino hitting something. It weakly interacts with matter.
Is it because their masses are very small, or is it because of a different reason?
Well, a couple of things. First of all, it has no charge. That helps, right? Being neutral, and it also it really only interacts with normal matter via the weak interaction process. or gravitation. But it's so light. The latest limit about how massive a neutrino is that the three flavors, right? The average of the three flavors, the electron neutrino, tau neutrino, mu neutrino, is less than 0.12 electron volts. So what does that mean? Well, an electron mass is around 511,000. So a neutrino is about 6 orders of magnitude less massive than even an electron, which is a pretty small in mass. So, and that's the upper bound, right? There's about a 95% confidence now of that thing. So if you say, well, what is that in terms of in more normal units? If you're doing kilograms, it would be less than about 2 times 10 to the minus 37th kilograms. I'm sorry, 2 times 10 to the minus 37. So 1 over, 2 over 1 with 37 zeros kilograms. They're pretty light.
We're on the quark page. What's the difference between an up and a top and a down and a bottom?
The quark,
mass,
I think, yeah,
and type. It's certainly mass is one of the things, and which family it's in. So there are, of the 3 families of fermion, up down is in the same family as electron neutrino. They tend to be the least massive of stuff. So when you get to family 2, they call it charm strange because physicists are sometimes creative in their names. The muon neutrino, the muon it decays, and it decays into a lighter mass. Same thing, the charge and the charm and the strange quarks are more massive, right? If you look at the mass on that thing, where the up and down is 2.2 and 4.7 million electron volts, the strange is around 100 or 96 million, and charm is around 1.28 billion. So you typically have things in 2 that are more massive decay into things that are 1. Electron is stable, muon is not. I think what's the half-life of muon? Is somewhere around.
It's like 22
curious
microseconds.
question. Like when more massive particles decay into less massive particles.
Yes.
Does that increase? Does that increase the entropy of it as well?
Close. 2.2 microseconds.
Okay. So I mean, it certainly will. It's a lower state, so it's going into a lower energy state. So the third generation of the top and the bottom are massive quarks. They're on the order of around 173. Like the top quark is like 173 billion electron volts. So it's a really massive heavyweight thing. The bottom is around 2.2 billion electron volts. The tau is again, tau is sort of lepton. So the quarks are one side. So if you look at this stuff, the quark families are one set, and the leptons are another set. So they're like, I wouldn't call them mirrors, but they're related.
Yeah.
And things in generation 3 decay into 2, and things in 2 decay into 1, and sometimes 3 go directly into 1, depending on what's happening.
Now, if I remember correctly, it's the first family ups and downs that make up the neutrons and protons of atoms.
Yes. So those are the more common things you stuff is the nucleons are made of up down. But right now what we're happening is that in this first second decoupling, before this era, the universe was so hot and dense essentially that the neutrons were being essentially bouncing around and interacting with batteries.
So right now, none of these have got married to stay together yet. They're all being their own single. They're all being single and bachelors.
The quarks have settled down to some, like they exist.
Yeah.
We don't have like atoms and stuff yet.
Yeah.
But
Because remember, the first 20, around 20 microseconds to the first second is when the quarks started grouping into these hadrons.
Yeah. So that's sort of happening, and then like kind of right after that, you have the neutrinos also. They decouple, but like in a sort of a different way. The universe is finally cool and dilute enough that they stop running into everything.
Yes,
I think that's what.
You call it thermal equilibrium. That's a good way to put it, because the thermal equilibrium kind of breaks, and the neutrinos stopped having significant interaction with baryon matter. Part because the universe is not as dense as it was, and so these things, because they're not, they essentially are the first things that kind of flee on their own. I mean, there were interactions, but because the universe had expanded so much and became thin enough, the neutrinos can actually get some distance.
Yeah, because the neutrinos have a vanishingly small probability of actually colliding with other particles. But before this point, the universe was so dense that a neutrino could travel a very short distance and go through an absurdly high amount of mass, so that even though the probability is almost nothing, it's going to hit something, but in just a matter of a short distance.
And so think about that 3,000 light years of lead, that
Mm-hmm.
material being squished down to something where a neutrino in a fraction of a second hits something, because it becomes so dense. That's really the I think a significant thing. Now neutrinos are typically created by various radioactive decays. So, for example, nuclei that the beta decay of an atom, or nuclei hadrons will produce it. Also, various nuclear reactions that take place in the star when the star is fusing generates neutrinos. And also, you can get artificial things like nuclear reactors, nuclear weapons, and particle accelerators can generate neutrinos.
Right.
They also get generated in supernovae, and we'll talk about that next session. Also, something about the spin down of a neutron star. These are things. Well, again, we'll talk about neutron stars next session, and then when cosmic rays strike things, and again, we'll talk about neutrinos showing up there as well.
And before we move on, what's the difference between a quark and a lepton?
They're fundamentally sort of different classes of particles. Quarks interact with each other via the strong force. Leptons also, I guess, like interact with quarks, but they go via the weak force. They're also they have a certain essence to them that is also conserved.
Mm-hmm.
Like there's a thing called lepton number, and it's a quantity that ends up being conserved that quarks like don't have, for example.
I guess you can also see in the image right there, like if you look very closely at the background, you see like these shades that encircle the gluon and the quarks, like denoting that the quarks interact via the strong force carrier, the gluon. And then you see another shadow that encircles the photon with the quarks, and also the electron, muon, and tau, I believe. And then you see you also see the Z boson and the W boson shadow encircling all particles. So you can see that,
except for the photon, right?
Except for the
photon and the gluon. Okay.
Yes.
They're
funny again. They're fundamentally different particles. But we want to focus back on right now is going on is that the big thing is neutrinos. That the universe has become thin enough that neutrinos are now not interacting with matter very much. Now the neutrinos that they have we have a lot of evidence of this from what's called the angular power spectrum. I believe if you go to the next slide, this we will look at this a bit more when we come to looking at the cosmic background radiation. But there are sort of angular sizes that we see in the universe that have these sort of resonances, and part of the evidence of this Big Bang process comes from the bumps that are beyond the first peak. Also, in this particular situation, that the models for the Big Bang process had predicted that the temperature when the temperature of the neutrinos at this stage should be around 1.95 Kelvin, and in 2015 they did the claim detection of the background of neutrinos. So remember, neutrinos are now able to go far enough to be able to detect it, and we can detect some of those early cosmic neutrinos today, and their temperature is around reported about 1.96 Kelvin plus or minus 0.02. So there's indirect evidence. There's indirect evidence from the phase changes of that cosmic background, that curve you see.
I don't think we've ever directly measured any C and B neutrinos, though. I think they're low enough energy. I think they might even be non-relativistic. So
the report came from a group in 2015 that claims that they have evidence for that. So there at least are claims about that.
Okay.
That being those being the case. And 2015 was reported that such shifts, that there are shifts that have been detected in cosmic microwave background. These fluctuations correspond to neutrinos almost exactly the same temperature as predicted by Big Bang models.
Okay. Yes. That sort of evidence certainly.
Yes.
So
basically, it is a very slight effect on the phase of the fluctuations. It's how they. So they're not directly detected; they're indirect evidence.
Okay. Yeah.
It's basically the fingerprint of the neutrinos left on the CMB, basically.
Yes. Mm-hmm. And so that was one of the interesting triumphs about the Big Bang model is this prediction that appears to be quite corresponding. So neutrinos decouple, right? They're no longer in thermal equilibrium. They're taken off. So should we go to the next? Go ahead.
I just want to say that this is directly analogous to what is going to happen later with photons. The neutrinos, that they stop bouncing into everything and they just keep on going straight in whatever direction they were going when the universe became transparent to the neutrinos.
Yes, because before the universe was dense enough that the weak interactions mean that their mean path was not very far.
We talked about that earlier before you got here, but we can do a quick review if you want.
We can go back for like one slide and quickly point out the neutrinos on that, like on the standard particle. Yeah, I think the neutrinos are on the bottom, right? The green ones. Correct. On the bottom. Yeah.
Yes.
The on the very bottom.
Mm-hmm. All right.
Okay, so let's move on to the lepton epoch, where we now are going to speed up. We're going to talk about the first 10 seconds or so. And in this lepton epoch, the temperature has dropped from around 10 billion Kelvin to only 1 billion Kelvin. And the energy levels typically are from the mega electron volts down into the 100,000 electron volts.
So how hotter is this than our sun?
significantly hotter. I think it's on the order of around 2.
Which part?
It depends. Like I think the core is like a trillion
And-
Kelvin, right? The core, or not? Maybe I'm mistaken.
It's in the millions. Isn't
Mm.
so? Isn't this around 3 to 4 orders of magnitude hotter than solar cores? One of the things, and another thing that here is that the vast majority of hadrons and antihadrons annihilate each other at the end of the hadron epoch, right? Because we were having these quarks come together, and we had like protons and antiprotons annihilating each other, and the leptons from that model are now in, and antileptons are now in thermal equilibrium. So the photon energy is still high enough to produce electron-positron pairs. So remember, E equals mc squared. You get energy that turns into mass, and mass comes back to energy. So very energetic photons can if they are greater than 2 times 511 kiloelectron volts, can turn into a pair of particles, electron and positron. So the universe is actually still actually hot enough to create create electron positron pairs, and also at this point starting to create neutrons, I believe, at this stage. So there are actually a small number of electrons around to sort of neutralize the universe, so that basically the universe is going into a sort of a neutral charge, right? We're no longer having pockets of charge that sort of equilibrate out, and neutrinos have taken off, and photons still are creating pairs of electron positrons. You're no longer having more massive particles being created and destroyed. We're now still at the range where we can generate electron positron pairs.
Landon, question. You seem to be implying that prior to this point, or there might have been a point when there were like areas that were not on average electrically neutral. I would have expected, on average, all of this to be electrically neutral sort of throughout. You don't
remember there is an imbalance in matter antimatter, and so you're going to have for example, an excess of protons, and so you'll have a charge, sort of a little bit of excess positive charge, but the photons are going to be also, there still is a small number of electrons around after these annihilations to sort of neutralize what the protons were doing.
So did the universe have a net charge that was positive and became neutral?
Because that small residue of electrons were needed to essentially neutralize, and that also came as an important part of the neutrino decoupling process.
Well, okay, that's interesting, because I was under the impression that charge was always conserved. I understand that the electrons weren't there, but that doesn't mean that. In my head, I sort of thought that it was a kind of a charge sort of soup.
Well, you're right and being confused, and it is a point of confusion, because in some ways both charge should be conserved, and also the fact of the hadron antihadron should have been balanced, right?
That's true. Yeah.
So in a normal citrus universe, the charge would be conserved and matter antimatter would be created in equal amounts. Obviously, that isn't the case, because we have an excess amount of matter, and we now have a case where now we have the universe going where we have an excess of matter, because the matter antimatter. What was it about? Like 1 part in 1.6 billion, wasn't it?
That's something that a part in a billion sounds.
Yeah, and so we have there was a little bit, for whatever reason, more matter than antimatter, and then we've got electron-positron pairs, but we also have charge annihilation that's occurring where the small residue of electrons charge neutralize the universe. So electron charge neutralizing says the universe wasn't charge neutral before. It's happening. That's happening now, and that's an important part of this neutrino decoupling that's occurring. That occurred at the first second.
Okay.
Also, you can also notice that the universe right now went from like 10 light years in diameter to 33 light years in diameter. Roughly speaking, like there are different estimations I found, but I found one of those estimations that point to this.
And somewhere in 33 light years is probably a reasonable set. And again, if you look at that wonderful graph of the you did on the lepton epoch, right? You see that one of the things that starts happening is that the neutrons are starting to begin to decay. They'll begin to decay, but they're not fully decaying. They're beginning to decay because there's a half-life there. But we'll get into that in the next.
I guess like before, like during the hadron epoch, you have like neutrons and protons were interchanging with each other constantly. Like they were at equal ratios during the time. But after after the time interval when we reach 1 second in the time interval, then the universe cooled enough such that this equilibrium was no longer happening. So then neutrons kept decaying into protons. So
and that's a big, and that's an important point because the neutron-proton ratio fell from 1 to 1 to 1 and 6, right? That is there were far more protons and neutrons, but you had electrons around to balance the protons in terms of charge-wise.
Mm-hmm. Like when neutrons decay, you also that also generates an electron, right? When neutrons decay, or not?
Now we don't have enough time for the neutrons decayed. The point is that in this early universe, it's this ratio of the energy is still high enough that photons can create these electron-positron pairs, and so leptons, the leptons, like the electron stuff, and anti-electrons, positrons, remain in sort of thermal equilibrium, but we're about to that's about to change, and some of it has to do with nuclear forming in the next set, but again, the charge ratio, the ratio of neutron proton went from 1 to 1 to about 1 to 6. Things are beginning to neutralize in that session. So
ready for next page?
Sure.
There. I thought for those who may not know what these numbers mean, I thought we'd go over a few slides of what each of these numbers mean on these elements, because they're starting to form now.
Yes. I mean, you probably have seen in chemistry like H2O, where the 2 is in front of and below H. In nuclear stuff, we use different corners. So as you can see in the upper left, if you see a number in the upper left, that refers to the atomic mass number. How many proton neutrons are in the atom. If you see one that's in the lower left, it's the number of protons. So helium is defined by having a nuclei with 2 protons. So helium will always have a 2 in its bottom corner.
But the top number can be different.
Yeah, generally the bottom number you don't see. I guess it's kind of redundant because the element symbol He in this case gives you that information.
Yep.
Technically, but this gives it to you directly.
Yes.
Okay, I guess it makes it also easier to see, like, oh yeah, helium has two protons. Sometimes you get to an atom where you don't remember how many protons there are. Like, it
and
helps, perhaps. Yeah,
that happens a lot. Like I work with strontium. The isotope of strontium that I work with most often is strontium 88. So you put 88 in the top. But there are other isotopes that have interesting properties, and eventually we're going to work 90. A lot with strontium 87. 90 sounds like something for the nuclear people to work with, not the atomic people.
But, yes.
But for the record, I do not know off the top of my head, actually, for sure, how many protons there are in strontium.
But this is the thing for me. For the longest time, I thought every atom had the same number of neutrons and protons, but they don't.
Yeah, strontium has an atomic number of 38, by the way, in case you forgot.
And, I totally forgot.
Yeah, it's one of those things. So in fact, the normal thing, like strontium has either the stable natural strontium is either, I think, 84, 86, 87, or 88.
Yeah. Yes.
And we're not at molecules yet. We're still far away from them.
That's correct.
Point.
Yeah. But so just give you a notion of all this obscure nomenclature.
But the number on the other side, it means something totally different than the number on the first side.
Yes.
Yeah. And then so far we've talked about 3 of the 4 corners, and then in the upper right corner, that's when you start to get that's where you put information sometimes about some of the electron orbitals. But then you also just have a whole bunch of extra notation for that too.
Yeah.
But if it's an ion, you put it there as well.
You've been around our corners. That's kind of the problem for there. So now that we're actually talking about atoms, I think it's time to move into the next era, which is this Big Bang nucleosynthesis. A nice mouse word. But here, if we go into the next segment, the thing is that in this in this particular era here, I guess. Well, let's first talk about the photon epoch, or do you want to talk about the Big Bang?
I made the slides in mostly chronological order. So first we will start with the nucleosynthesis, and then we continue on with the rest of the photon epoch. Yeah.
So in the nucleosynthesis, this is really occurring somewhere between the first 10 seconds and the first 20 minutes or so. And it is responsible for building a lot of the current element mixes today. So in this process of the nucleosynthesis, so the temperatures have gone from around 1 in Big Bang nucleosynthesis time. We're going from 10 seconds to about, let's say, 1200 seconds, 20 minutes. Temperature drops from about 1 billion Kelvin to about 10 million Kelvin. And energies go from around 100 kiloelectron volts to around 1 kiloelectron volt. So a couple things happen. First of all, about the protons and neutrons begin to bind together, right? The universe is cool enough that protons and neutrons, atomic force can start lumping them together. And so by mass, we have formed about 74% hydrogen and about a little bit less than 26% helium by mass, right? There was also
one thing we can also mention is that because the protons and neutrons are now able to bind, that stops the neutron decay. So now the ratio from 1 to 6 is stuck, basically.
Yeah. Well, it's actually fortunate because otherwise we were in the situation where we're getting now to the point where the half-life of neutrons would come into effect. But when they are under the influence of the strong nuclear process, then they form stable cells. So we formed about 70%, 4% hydrogen, about 26% helium. We did form small amounts of deuterium and helium-3. We also formed real trace amounts of, but that trace amounts of helium-3 of hydrogen-3. There's trace amounts of tritium. That's hydrogen-3.
Yeah.
It's a proton with 2 neutrons. So,
The
70%
hydrogen
by
isotopes have
70% by mass were a single proton. About a 100% had a proton and neutron stuck together, deuterium, and really trace amounts like 1 part in 1/10 billionth was a proton and 2 neutrons. But those tritium decay into helium-3. There's also a little bit of beryllium that gets formed, and it decays into lithium. So out of the Big Bang nucleosynthesis, we have mostly hydrogen, a fair chunk of helium, and a tiny bit, like 1 part in 1/10 billionth by mass of lithium. That's it. Anything else is so vanishingly small. I mean, yes, there might have been a carbon atom form here or there, but it's so vanishingly rare and small that it really didn't. You really can't detect it.
Yeah. So somebody in the live chat also asks about this, like the isotopes of hydrogen has special names, like most hydrogen only has 1 protons and no neutrons. I think that's called protium. I think so, right?
No, or just hydrogen.
Yeah, I didn't even know there was a name for it.
But yeah, it is. I mean, that's. I mean, the deuterium tritium is kind of unfortunate.
Yeah,
they have their own symbols, because I think they just should use H2 and H3, but that's.
Well, 2H and.
Yeah.
Right.
So
deuterium is 2H and tritium is 3H. Yes.
So 2H would be a neutron and a proton, and 3H would be a proton and 2 neutrons.
Yeah.
Yes.
And so again, 74% by mass was just a single proton. 100% was a proton neutron, and 1/10 trillionth by mass was a proton and 2 neutrons. But that quickly decays into helium-3. And then there's also some beryllium-7 actually gets created as well at this stage, and that also decays into lithium. So
do neutrons decay into protons, or do protons decay into neutrons more often?
Protons do not. Protons on their own are stable. As far as we can tell, the lifetime of protons has a lower bound of something like 10 to the 34 years.
Yes.
We have looked, and we are still looking to see if they will decay, but so far we have no compelling evidence that protons decay. Neutrons decay with a half-life. 3 isolated neutrons decay with a half-life of 10 minutes.
Yeah.
And they decay into a proton, an electron, and an electron neutrino.
Yeah, and that decay is if they're not under the influence of the strong process.
And real fast, because this is way in the future, but this decay is how geologists figure out how old rocks are nowadays.
From much larger atoms than these.
Yeah, not these. We're not anywhere close to that.
Like with large atoms, you have like the decay chains, and with that you can do very precise dating. Yeah,
really important to say that right now the universe is mostly hydrogen, a corner of helium, and then traces of lithium. That's it, right?
Yeah.
The universe is around 300 light years in radius by the time we're at 1200 seconds, and the density of the universe now is around, let's say, 0.3% of density of air at sea level. So if you look at the density of air at sea level on Earth, the universe is about 0.3% of that density. So most of the But most of the energy in the universe is actually in the form of photons, electromagnetic radiation, right? The ratio of and so at this point, the universe is actually very close to homogeneous.
Right. It says the observable universe at this point is 100 light years. Is only 100 light years. Is that still
observable universe about 300 light years?
Is that still smaller than our what we think the size of our own galaxy is?
I'm not going to answer that because I think that's I know what you're trying to say, but I think that's misleading to compare stuff then to stuff now. It's so it's so different. That we're talking about right now the observable universe being in the order of what was it 60, 70 billion light years. At this stage is only around 300. So the universe is much more compact, but still compact enough that it's thinner than air at sea level. But one of the things that happen is that when the universe energy dropped down to around 30 kiloelectron volts, you no longer had much in the way of nucleosynthesis, right? You're not generating these. You're not taking these hadrons and slamming into form atoms. So the primordial abundances of the universe are now set.
Also, we've been using the names of atoms to talk about this, but these are just the nuclei. Like there's no electron that, not even like one, generally. Yes. I mean, there might be like one in the whole universe, but it would have a mean lifetime that would be vanishingly small, and it would immediately break away.
The electrons are too hot. They think it's too hot for atoms to form, chemical atoms to form. And so we have a bunch of protons. We have a bunch of pairs of protons and neutrons that we call helium nuclei, alpha particles. We have a small amount of proton-neutron pairs that we call deuterium atoms. And we have a light amount of lithium.
So there's no official atoms/elements yet.
This is nucleosynthesis. This is the synthesis of nucleons, not atoms. There's no chemistry.
We only have the nuclei.
There's no rocks. There's no really, and also stuff hasn't really decayed enough. I mean, certainly, for example, the case of if there was trace amounts of a proton and two neutrons came together to form what we call a tritium nucleus, it quickly decays into helium-3. It eventually decayed into helium-3. So today we see most of the helium today came from this era. Most of the helium that you can see in your helium balloons or whatever have most of the helium today, I should say, not in helium balloons, but because helium balloons come from rapid decay in the Earth. Most of the helium today in the universe came from this era. It is cool enough for deuterium to survive. Here's another thing about stars, right? Is that the universe is cool enough that a proton neutron can bind together, strong force, but not hot enough for those nucleons to smash together to form helium. We're not having fusion of atoms at this stage.
Yeah.
That's a pretty important thing. It's cool enough for the survive, but not hot enough for the deuterium to fuse.
One question: during this process of nucleosynthesis, was that fusion or a different process?
No. This is my point I'm trying to make. Is that at this stage, the universe is cool enough for a deuterium, hydrogen, a proton-neutron pair to survive, but the density which that would have been able to fuse into helium would have created a temperature which those nucleons weren't forming in the first place, right? You don't have fusion because the universe is too cold, right? The temperature have dropped down below, around the temperatures have dropped around 10 million Kelvin. So you were below the thing where stuff happens.
Yeah,
And
and
so
it's
the
also
the process that creates the helium here is different from how the sun creates helium, basically. Yeah, all right.
Yeah, and it's a combination of temperature and density. The center of the sun, the number I'm remembering for the core of the sun is about 5 million Kelvin, but the density is much, much, much higher.
Yes.
Than it is at this time. So
right.
I think, and I actually, this is something that I'd like to learn more about, but I think it's a little bit. It's not like these nuclei are like condensed out of a quark gluon like plasma soup, is it?
No.
Well, you see that the hadron epoch was between the first 20 microseconds to the second. That's where the fundamental interactions began to form, and that's where you started to have sets of 3 quarks forming hadrons. So the hadrons started coming together in the early part of the first second. This is a case where you've got hadrons in the form of protons and neutrons slamming together and being dense enough that the strong nuclear interaction is starting to lump them together.
So the quarks. Oh, sorry.
I was going to say that what you just described, Landon, is, I think, technically a form of fusion. It's just that
it's not stellar fusion.
It's not. Why is it not stellar? Why is the actual process different? Like if you were to draw like the Feynman diagram for it.
Okay, in that sense, the answer is yes. It is this. You would have a similar Feynman diagram for it. What's different is the heating up and re-densification, and that's going to be occurring when we start talking about structures and stars in the next episode.
Yeah, the thing that turns this off is that it gets too cold for that to continue happening.
Yes.
Mm-hmm.
And
also, one last question I have on this slide is like we see the atomic weight of 1 and a few of 2 and a few of 3 and many of 4, and then also a few of 7. But we don't see any atomic number of 5 and 6. Is there's a reason for why we don't see any atomic numbers of 5 and 6?
Stability. Mm-hmm. I think like helium-5 has such a short half-life that a photon can barely cross its nucleus radius before it decays. I mean, isn't like 10 to the minus 20 second, minus 22 seconds. I mean, it's got an absurdly fast rate. There was at one time there was debate whether or not helium-5 even exists, right?
Yeah, and that's a debate because like if something doesn't exist for long enough, if its lifetime is shorter than its energy, which is a concept that makes sense when it does, then like it's not really even like a well-defined kind of particle.
If you could never see it, right? Because you couldn't get a photon to go across its nuclei or interact with it, did it really exist, right?
Yeah. What you would have is sort of a vaguely resonant condition of like arrangement that might be a little bit more stable than just,
But if you talk about helium, and you talk about helium, isotopes, or other compounds, right? That again, helium-3 and helium-4 are stable parts of stable isotopes, right? But there is but there are other isotopes. We've detected 2 helium to up to 10 helium, right? So we've detected a pair of protons together up to a pair of protons with 8 neutrons. and those things have such a short half-life as to not be much around much, right? I think it's like 2 zeptoseconds and stuff, where it's vanishingly small. So you asked about where the 5 and 6, and from the helium side of point of view, the 5 and 6 are just they're now helium-6, I believe, has a lifetime of around 0.8 of a second half-life, if I recall correctly, about 0.8 of a second.
I do not know.
And so it is a also, but again, the time period we're talking about is between 10 seconds and 20 minutes. So helium-5 decays almost instantaneously. It basically kicks out a neutron. And helium-6 decays into lithium-6 and helium-4, but that was so vanishingly small as to be sort of undetectable. But when you start getting into case of when you're talking about isotopes of lithium, on the other hand, as if I recall correctly, and again, I'm going to go back to I'm trying to image my chart of the nuclides. That's how chemists have the periodic table elements. Nukes people have the basically a two-dimensional chart of isotopes, and helium or lithium does have isotopes, but here the main one that's being formed is lithium-7 coming from beryllium form. And beryllium, remember, is hydrogen, helium, lithium, beryllium. Beryllium is 4, right? So you probably have helium things coming together, kicking out a neutron, but that beryllium-7 decays into lithium-7. Did I get that right? I'm doing it from memory.
I don't know.
Natural lithium is lithium-6 is certainly
the most common, right?
I think it's about 7.5% of natural lithium is lithium-6, and
okay.
lithium-7 isn't it the other one that's
I've never I know more about a lithium's S-wave scattering length than I know about its natural abundance.
Mhm.
And lithium is the 3rd element, right? In the chart.
Yes.
Yeah.
And so people are yelling at us saying blah blah blah, but yes. So I'm looking now at my table. Lithium-6 is stable. Lithium-7 is stable, and the abundance is around 92.2% to 98.1%, depending on if you talk about population or range. Is lithium-7. So most of it lithium-7, and about 2% is lithium-6.
Yeah. If you want a kind of big picture sense of why this is where it stops, why doesn't it stop at carbon? Why does it stop at lithium, basically? The sort of way I think about it is helium-4 is like crazy stable. It is a very favorable state to be in. It is much more stable and much more likely to occur than any of the sort of combinations that are a little bit higher than that. You have to go up like an order of magnitude before you start to find anything else. And really, nothing is quite as stable as alpha particles. Like they're yeah.
Now
so that's kind of a reason.
Now I mentioned about saying that beryllium-7 decays into lithium-7. A little bit caveat that the half-life of beryllium-7 is around 53 days. And it usually decays by electron capture. So if we're being scrupulously honest, during this period of time, there is lithium-7, or beryllium-7 being formed. It hasn't decayed yet. It'll decay shortly. And it typically decays by capturing electrons. We don't have atoms for it to even capture. It's probably grabbing occasional electron and finds around there. But at this stage, we're only at 20 minutes. The beryllium-7 that's formed is going to be decaying in a couple of months. The beryllium-9 is stable, but beryllium-9 is too much energy it's too difficult for these hadrons to be during nucleosynthesis to slam together to form stable beryllium.
During this time, it wasn't hot enough and dense enough for that to happen. Basically,
correct.
That can only happen in stars.
And beryllium. The other isotopes of beryllium have such a short half-life that they're not sticking around, or they're not forming. So in this era, we're talking strictly right now, and sticking to the 20 minutes, we have hydrogen in nuclei. There's protons. We have proton neutron. We have proton neutron neutron. Because if you're again being technical, that tritium nuclei hasn't decayed yet. It will.
The lifetime of the half-life of tritium, though, is on the order of a couple of years, maybe like
12 years, 12.7 years.
I have on my keychain a little glowy thing. I can't even find it now. Maybe it's but I have a vial of tritium on my keychain because it's alpha decay. It's not getting through the little plastic that it's in. And I've had it for about 6 years now, and I've noticed it's gotten substantially dimmer.
So you said alpha decay. Don't you mean beta decay?
Oh yeah. Sorry, my bad. Yeah, I can't alpha decay. There's not enough there.
Yes. So again, in this first 20 minutes, we have protons. We have proton hydrogen. We have proton neutron. We have proton neutron. They'll decay into helium, 3 helium. We have 3 helium directly. We have 4 helium because that's a nice cluster. You'll find these nucleons have these groups that likes to form. Just like in chemistry, you have these electron shells. Well, there's if you will, there's sort of nucleon shells, if you will, inside the nucleus.
There
is some beryllium-7, right? But the beryllium-7 there is beryllium-7, but the beryllium-7 has not decayed yet. It will decay. Beryllium will decay in around 2 months and form lithium-7. So the big thing that comes from this epoch is that, unlike what's going to be happening in stars and with life cycle of stars, which happens next episode, we have the masses today. Most of the hydrogen you see today came from this era. Most of the helium today did not form in stars, but came during this Big Bang nucleosynthesis era, between 10 seconds and
although as you mentioned before, the helium that we have here on Earth comes from decay from the crust, right? Yeah.
Although there is some primordial helium on Earth.
Anything else on this page we need to talk about before we go to the next slide?
I use this image to basically summarize 3 epochs. Like here on the left, you see the hadron epoch where the protons and neutron ratio is equal. And then we move on to the lepton epoch where the neutrons begin to decay into protons. So then you have the 1:6 ratio of proton to neutrons. And then during the photon epoch, during nucleosynthesis, then you have the formation of nuclei that stabilizes the neutrons. So now the ratio between protons and neutrons remain fixed, more or less. Yeah.
Yes. So shall we go to the next fun epoch?
I think we are still in the photon epoch, but we just continue on in the photon epoch.
Yes. We'll continue. So we'll go back because these are sort of overlapping the effects. pardon us for going back to 10 seconds again, but in this situation, the universe is dominated by radiation, by photons.
And then we finally jumped a significantly amount of time now. We've gone from
Well,
seconds.
we start with 10 seconds, so we're still at
Yeah.
the 10 second thing at the beginning of stuff. We'll get to a bit more.
I guess I could have changed the time interval, because from 10 seconds to 20 minutes, that was nucleosynthesis, but now we have moved past the 20 minutes mark. Basically.
Okay.
Yeah.
So let's talk about 20 minutes going on forward. And here the temperature is too low to create electron-positron pairs or other massive particle pairs. The temperature is too high for electrons to actually bind to atoms. So we don't have atoms, we have nuclei, we have electrons flowing around, right? The universe is pretty much charge neutral, but we just have a soup of nucleons and electrons going around.
Plasma, plasma phase.
Yeah.
Mhm.
And so there's no atoms because it's too hot. I mean, the temperatures starts off at around 1 billion Kelvin, and it isn't until you get around starting to get around in the 10,000 Kelvin range that you're no longer dominated by radiation. Right? It takes the Big Bang process about 47,000 years before the universe is not dominated by these energetic photons around.
So you're saying that. Oh, so what do we mean by that when we say that it's photon dominated? What I understand that to mean is that yes, you have electrons that are moving around, and yes, you have nucleons and nuclei that are moving around. Those things have energy because they're moving, but mostly because they also just kind of exist.
Yeah. Also early on, the photons have enough energy to actually break apart a deuterium nuclei, right? One of the things why there's not much deuterium around is that at the time early on in this photon epoch, the photons would just basically smash and break apart the deuterium.
I did not know that.
And so it's what's called photodissociate deuterium. So that basically these atomic nuclei are formed quickly or separated back into proton neutrons. One of the reasons why there's very little deuterium. And this is another reason why you don't have this situation. You don't have the photon load inside a core of a star. The star isn't shattering its deuterium into hydrogen and neutrons in a stellar core. In this area early on in the photon epoch, where again, it's going to take around 47,000 years before the universe expands and cools enough that photons are not being destructive, right? Once the thermal energy drops to around 30,000 electron volts, nucleosynthesis basically comes to an end, and the primordial abundances are set. But yes, the big thing is that by the 10-second mark, there are fewer hydrogen photons available to dissociate deuterium. So deuterium starts to stick around more and more and more, and heavy atoms form through a fusion-like process where you'll get the tritium, helium-3, helium-4, and trace amounts of lithium and beryllium, which decays into lithium.
But most of the energy that's around here is not in the particles that are moving around and have mass. It's mostly in the photons. There's way more photons than there are massive particles, right?
Yes, very, very good point. But then something kind of wonderful happens towards the end of this epoch. Although we want to move on to I think one of my favorite parts of favorite times.
Yeah, well, I want to say so to lead into that. During the photon epoch, even though like photons, which light is photons, are sort of the thing. The universe is opaque. those photons don't travel very far before they hit a free electron or a
Scatter,
nuclear, or they scatter off something, and the electrons and protons that aren't paired up, they interact very, very, very strongly with photons, and so a plasma will be much more opaque than
it's a fog. Oh well.
Yeah, it's exactly. And if you had been like transported back there at the beginning of the photon epoch, you'd get vaporized. At the end of it, you'd still end up dead. But 4,000 Kelvin, I can imagine a building like a submarine or something that would make you last for a quarter of a second, and it would look hot, but at 4,000 Kelvin, it's not going to look totally white.
Yes.
It's actually going to look like yellow.
I think you can point at the sun. Like the sun itself is a ball of plasma. So you can see the sun because the space between the sun and you is transparent, basically. But the sun itself is not transparent. You cannot see through the sun. Yeah. Even if you have magic goggles that allows you to look at the sun, you still cannot see through the sun. Basically,
photons do not go through the sun.
So have you ever seen a basic plasma kiln, right? Very high temperature kilns. What you start seeing, you start losing the ability to even see objects. You just start to see this glow. It looks like a neon sign. Basically, you just get glow, right? And that's because, again, the photons are being scattered off of charges, and so you get that like a fluorescent tube. It is fluorescing, but something happens after around 378,000 years. So shall we go to the Big Bang flash? Okay, in here, around 370,000 years, something very special happens. The temperature drops to the point where protons can capture electrons and form neutral hydrogen atoms, right? Here we got to start getting atoms. We don't have a bunch of subatomic particles. We start having atoms. Now, they call it recombination because usually in normal things, you have a plasma that's condensing out and forming atoms. Call it recombination. It's really a misleading term, but because essentially proton electrons hadn't been combined before, but
it should have been called combination, not recombination.
Well, that's why we call it the common thing now. So it's called the Big Bang flash, because what happened was the universe went from this glowing plasma fog to transparent. The protons grabbed hold of electrons and formed neutral hydrogen, and the photons took off. And today, when we observe the universe in the microwave, we see the leftover radiation, basically the echo of the Big Bang process. It's one of the more triumphal things about the Big Bang models was that they predicted that we would see this cosmic microwave background radiation. And it has been redshifted from today's perspective, it's redshifted around 1,100 times. So it's been stretched out to the point where the photons appear as microwaves. But back then they were hydrogen. Now, do you want to talk about how hydrogen actually does this? Because there's a little bit of tricky bits here.
Yeah, it is. So hydrogen, you can compute the sort of temperature that you would need to have if you just had like a hydrogen atom on its own. How hot would it have to be in order for its electron to be removed from it? That temperature is actually really like pretty darn high, a lot higher than the temperature of the universe when we had the flash. And the reason for that is because there's actually a lot of, like, you have to look at the full sort of treatment of what's going on, because you don't just have an isolated hydrogen or something like that's trying to be hydrogen. It's in this photon bath with everything. And for a long time, any time you would have an electron that would go and pair up with a proton and form an atom, there would be a photon very nearby that would just whack it and dissociate the two.
Yeah, and radiation is scattering around. By the way, I remember the term is called Thomson scattering.
Yes, exactly.
Yes,
it's basically just directly scattering off of the free charges, and that's how everything is being maintained in thermal equilibrium. Everything is basically the same temperature everywhere at this time. However, eventually you do, as things expand and get colder and colder, you eventually hit a point where you do actually have a pretty good chance of of an electron and a proton pairing up. And when you do that, that reduces the amount of free charges that are still available. And over a pretty short amount of time, I think on the order of like a few thousand years, like it was more than 100 years, but it was less than 100,000 years.
Yes.
I think it was less than 10,000 years. I think about 1,000 years is maybe not a crazy sort of time frame for when basically all of the electrons and protons were free to when they were almost all paired up together.
Yeah. After this Big Bang flash, there was that basically the free electrons and protons were about only by a few parts per 10,000 at this stage. They were fairly rare, not impossible, but fairly rare. Most hydrogen atoms have been formed, and there's only a small amount of naked protons and electrons.
Yeah.
Right.
Yeah, according to my,
you have to go from like, if you have 1 in every 10,000 electrons is free, that is still a high enough it's still opaque at that point. That number has to drop to a pretty, I think there was a graph actually. Yeah. I think that might.
There's a few parts in 10, and a few parts in 10,000. So it's more like, that the vapor, you've got a water vapor that's been now condensed into droplets. Mm-hmm. There's a little bit of water vapor still around, but mostly droplets, right? There's a little bit of free protons and electrons around, but most of it has condensed into neutral atoms. Why? Because the universe is cooled enough that proton can grab hold of the electron and form an atom.
I think it's a good analogy with humidity. Even most air is still humid at some point, but then when you reach a certain point of humidity, then you cannot see very far, basically.
Yeah.
You said at this point, true elements have formed now of all three of the 2 or 3 of the things. This is a while before
helium formed a bit earlier. But photons kept knocking them out. And so around this time, both neutral hydrogen, nuclear helium formed enough that the photons aren't knocking out the electrons.
Can compounds or molecules form yet?
No.
I did find that you like some point you can have helium hydride, basically helium with a charged hydrogen, and that was the oldest molecule, basically. Yeah.
It's not the density is such that you're not really having those kind of bonds get broken at the high temperatures around 4,000 Kelvin.
They are transient. They are transient compounds. Yeah.
Now there is a thing about there's a fine detail about how hydrogen actually what happens, how it captures. You want to talk about that, the ground state and that sort of thing?
You actually might. You explained it pretty well when we were discussing it a couple weeks back.
So if you look at the ground, so atoms have these electron orbitals, right? And the neutral hydrogen at the lowest ground state is a proton with an electron in its first orbital. That ground state is actually forming that ground state directly is very inefficient. Usually, what happens is that because again the universe was hotter, the proton would grab hold of an electron and be at one of the higher orbitals, higher energy states, and then that would end up emitting photons to drop to the lower state. So a lot of there's some confusion about this, but the main pathway is that you get what's called from the 2p state by emitting a Raman alpha photon. Then those things would always be reabsorbed by another hydrogen atom that's in the ground state. The better way is to form the 2s state by emitting 2 photons. That's slow. So the fast way of stuff, the photon that would come out would be absorbed by another hydrogen atom. It took the slower mode which was from the 2s by emitting 2 photons to get to neutral there. But again, that's part of that multi-year process you're talking about of it cooling down. Now, it's important to understand it. And do we have a picture of the of a microwave background?
I think so. Yeah.
Yes.
Yes.
Yeah. So
like as you mentioned before, the moment when the universe became mostly transparent, the photons were free to travel, and those photons are the microwave background radiation.
So now, the first image up there, Kobe, was the first sort of satellite that they're now Penton Wilson at Bell Labs had actually detected photons, microwave photons through their microwave detector at Bell Labs early on in the 60s, and Kobe was the first satellite launched to do a full-scale sky map.
So are these
WMAP was a bit more detailed, and Planck was even more detailed. So those 3 images you see there are sort of transition from we detected microwaves to we have a map, but it's kind of crude to a much more detailed map.
So is this when each picture was taken? 92, 2003, 2013? Is that when the pictures were taken?
I think that's when they were published.
Those were the results of those missions are published. So again, the first thing and Wilson got the Nobel Prize for detecting microwaves. They were trying to the telephone company was trying to look at using microwaves to transmit voice signals over long distances, and kept finding all this noise, this static hiss. And so these 2 Bell researchers tried to figure out what's the source of this noise and could they do something about it. And they ended up discovering that essentially the noise, this microwave noise, was all around the sky. In fact, if you have an old analog TV set where you can turn the tuner and you turn it between stations, and if you remember seeing, or people have been seeing the old when the TV would go off, the station would go off the air, you get that static fog, the static thing on the tube. About several percent of those little spots are actually photons from this Big Bang flash that you can still detect it in down in that microwave region. Kobe was the first spacecraft specifically designed to map in detail the microwave, and those colors you see there are because the Big Bang flash did not happen at an instant. It turns out the universe was not perfectly uniform temperature. There were some parts of the universe that were just slightly hotter than others,
and we mean like
slightly colder.
And we mean like a part in 100,000 on the roughly, right?
On the Kelvin scale.
Yes.
Yes. Because we're using
and so the difference between Kobe, WMAP, and Planck is the telescope's angular resolution, right? And so why was there were parts that were hotter and parts that were colder by a few parts per million? The answer is because there were sound waves in the universe. The universe was not completely, perfectly uniform dense. There were sound waves moving through the early universe. And where they're compressing, it was slightly, just tiny, tiny bits hotter. So it meant it went neutral just a tiny bit later than other spots. The way to think about it is that the microwave coming from that spot, because it occurred earlier or later, is slightly red shifted or blue shifted relative to the peak.
Now, was this where they killed all those birds, trying to get not the birds with the thing? They killed them all the birds to get the signal clear.
No, they're not killing birds. They put up screens because Penzias and Wilson thought that perhaps there was a interaction with bird poop in the microwave.
Because Penzias and Wilson were not looking for this.
They were trying to eliminate it so they could have nice telephone signals communicating by microwave.
There was a group that was going to be looking for this. Penzias and Wilson were not. They concluded after sort of a year of trying to rule everything else out, they were like, that's when they sort of realized the effect had been predicted, but it wasn't a thing that a lot of people were looking for.
And so they perfected the microwave receivers, right? Bell Labs was working on saying, well, gee, if we could use microwaves, these point-to-point communication, to transmit telephone signals, we don't have to string these copper wires. We could just do point-to-point stuff. And when they started building more efficient receivers, they found that was all this static hum, static hiss. And like, a stereo or your car stereo between two radio stations, you get that, right? That's what they were getting. And so they come, hey, what's the source of this? Could we have like a frequency to block it off? Is it because something is creating? And even they thought maybe the problem was that chemical reactions or things with bird poop were causing some of this glow to occur. And so part of the thing is that Bell Labs they were able to build really good microwave transmitters and receivers that are able to actually do this measurement and said, hey, look, this hiss we see, which is making it difficult to have nice, clear telephone communication through analog communication through microwaves, is coming from the sky. I said, oh boy, Big Bang Flash, predicted by the model and detected. And in fact, the frequency red shifted 1,100 times corresponds exactly to this business of these decoupling. Again, it's a more complex process than just simply forming neutral hydrogen. The hydrogen formed with electrons at higher orbitals. Yeah. And the main thing was the 2s went down by emitting 2 photons, and those at a much slower process, and those photons are the ones that turn into the microwave background, because the 2p stuff, lemon alpha, kept getting absorbed by another atom.
Vandalia.
Yep.
Put me up. So here I have a nice little hydrogen atom, and apparently my screen is reversed, right?
Mm-hmm.
Yes.
Okay. Well, I didn't know that. So you can't. That says ground. Hydrogen has its ground state, and then you go up and it has its excited states, and then it has more excited states, and eventually these excited states just merge, and then up here the electron is just free.
Yep.
And if the electron is here, for example, it takes very little energy. It only takes that much energy.
He's pointing to the second line above ground.
Hey, real fast, Tapioca. Go into settings, go to video, and mirror camera.
Yeah, and for those listening, he was pointing to the ground state at the bottom.
Yeah.
And there's a line apparently about a third way up, and there's a third line that's up even higher for those that are listening and not seeing.
Yes. Yes. So if the atom is on the third line, it's at the which is
2s.
So yeah. Well, the 2s is, I think, right here, right? It's sort of like a degenerate one. So okay. You have it, and you need some energy. The process from going from this state to the ground state is very inefficient.
Yes.
And it requires releasing 2 photons at the same time, and just the probability of that happening is very, very, very low. So generally, things don't really decay that much, which means the electrons are always up here, and it only takes this much energy for them to get booted off and stay as free electrons. That's why it really depended on when it got cold enough that they could finally drop down here. And once they drop down there aren't photons really around that are going to excite them back up, because going from here to here is just as inefficient as going from here to here, except you need to get hit by 2 photons from different directions. Whereas when you're going down, you can just emit those photons.
And so the 2p state dropping is the problem is that photon would get absorbed by another neutral hydrogen atom and kick it back up again.
Yeah, exactly. So
there's been some confusion about the temperature. Those have different temperatures at different times, but that's a bit of sort of chemistry, because I know that there's some folks who prefer dogma over science get confused about this transition thing. But
they look at it and they hear that the ionization temperature of a hydrogen is 100,000 Kelvin or something like that. But we didn't have recombination until like 4,000 Kelvin. It's because it's not that simple. You actually have to look at how do you actually get the electrons down into that energy level?
Yes.
And that process depends on things like the fact that there is a particular transition which is mostly forbidden.
You mentioned dogma.
It's like a chemical reaction where you have to go uphill to the transition state, and then after that point it's downhill basically.
You mentioned dogma. Does creationists talk about this time period at all?
There's some people that are confused, but I would refer you to like channels like Dapper Dino and so forth that could talk about some of the. He sometimes covered some of the creationist confusion. But back to here with this notion of the Big Bang flash and effectively hydrogen going neutral, but not instantaneously and having lumps. The angular size of those lumps is part of that power spectrum, and that's another thing that the Big Bang model predicted. The grainness of the Planck, for example, image is matches very well the model of how the universe would essentially condense, if you will. The fog goes to clarity, in that sense. But I have to say, from the I was in the audience, American International Study audience in 1992 when the COBE results were announced, right? And people were waiting, what happens. And this, if you see in this graph right here, you see that curve, that sort of lopsided bell curve. That's basically that's essentially showing you sort of the black body distribution of the frequencies. When something is a certain temperature, it glows at a certain frequency, but it's not a single line; it's a spread. And this is showing you
some photons have a longer wavelength, some have a shorter wavelength, but there is like a maximum where most photons are at a particular wavelength.
Yes.
The top
and
of
the maximum peak corresponds to the temperature. In fact, it's called the black body curve. Yeah. And so the question was, what would when they measured the light-gray background, what would it be like? And so the guy throws up saying, here is the predicted temperature at 2.73 degrees Kelvin, and and put up a plot that has that sort of, it was black, but like that red line. And they said, here is the what COBE measured, and you didn't see anything. And they said, and here are the error bars added to it. You didn't see anything. And he said, the reason why you're not seeing something, it's not a slight defect. I have to zoom way in because the error bars are so tiny that they are less than a pixel. At which point, the audience, standing applause, standing ovation, because essentially, it was one of the big triumphs of Big Bang process, which was that the thermal temperature of the thing, and the peak was predicted with the redshift. We know now from these transition things what the temperature is for the inefficient ground state, 2s ground state. We know what that temperature is. We know what the frequency is, and then you shift that down 1100, and it matched exactly what this curve was, and it was extraordinarily close to essentially a black body curve. The universe was a really nice black body, and it's now today it's cooled down not to the several thousand Kelvin, but 2.73 Kelvin, and the microwave curve follows that curve in a very, very great detail.
It's also one thing you can mention is that like today when you look at the night sky, the backdrop of the universe is black because your eyes cannot see microwaves.
Yeah.
But if you were to travel back in time during the time when, like, right after recombination, the universe was like about 4,000 Kelvin, which meant that the universe was not black. It was like a deep orange.
Well, you see that square up there?
Yes.
That's the color that you would have seen.
Yes.
The sky would have been that color because of the glow of stuff.
Of course, you would have been burned to a crisp at 4,000 Kelvin, but it's still, it would have been bright orange.
But not instantly, though, right? Like, you can imagine building something that would let you, like, survive a little bit. I mean, you don't have anywhere to put the heat, so eventually you're screwed. But, these are we use higher temperatures in manufacturing certain things. Not that often. It's still pretty hot, but like really, really high temperature, like arc welding and stuff, I think easily is much hotter than this.
Mm-hmm.
So the big thing is that so back to the Planck epoch, in the lumpiness of that thing, and again, we're talking about extraordinarily fine changes in temperature, getting order about 1 part in 100,000. That the lumps there are extraordinarily important, and we're going to talk about them in BE3. But that picture you see in Planck is the oldest picture you can ever see in this universe, right? That's where photons stop, the path of photons stop. Anything before that, the universe was this transparent plasma glow, and you couldn't see things, you couldn't see structure. When it went neutral through that process that took a couple of years, around 378,000 years, when it went neutral and the Big Bang flash that occurred throughout the universe, then we have the first we can see, you could actually see the first stuff, right? That's important to kind of realize, is we're really looking at what you can actually see at this stage.
Are we ready for the final slide?
Sure.
Any more things on this thing you talk? Anybody questions for this slide real fast before we go on?
I would say that this is probably one of the big triumphs of cosmology, and one of the strongest evidences of the Big Bang process was there. It was something was the Big Bang process predicted we should find. We found it. Now we found it. We found it exactly where we expected it, and we found it in extremely close to the frequency temperature that we expected. And congratulations to the Bell Lab scientists for first detecting it, and to these wonderful people of COBE, WMAP, and Planck, because a lot of what we're going to talk about in the next thing comes from the incredible science that these 3 missions did.
I gotta make a joke. I gotta make a joke real fast now. Move over, follow Rome. Move over, follow the Bronze Age. This is the Dark Age.
Yeah.
So and I will point out, Dapper taught me that the term Dark Age from history is not favored by modern historians. They prefer the term early Middle Ages. And if you want to get Dapper's feathers heckled up, talk about Dark Ages. However, we're not talking about this era in history. we're talking about a true dark age in the universe. What do you mean by dark age? Well, at this stage, once the photons are freed, we have this Big Bang flash. There isn't really anything else in the universe that's glowing, that's creating new photons. The photons were bouncing around inside that plasma. Hydrogen went neutral. Photons went whee, and nothing. Big, black, dark, nothing.
It took a few, probably 100,000 years to go into that state because you need to expand so that those photons stop being visible light. But that would happen. That would happen. After
it's like in my notes, it says like after 3 million years, the CMB redshifted to outside the visible range. Basically.
Yes. Yeah. Would have been infrared and keep sliding down. Yes.
Yeah. So when the universe was 3 million years old, then the universe was basically black at that point.
Yeah.
Sure.
And at 2 million years, if you had looked, it would have looked a very, very dim, deep red, for example.
Yes.
So it was a sort of transition, but by 3 million, that's not quite a factor of 10 older, which means a factor of 10, I think, in expansion, and roughly a factor of 10 in redshift. So,
and in terms of era, we're now in the stage where we're dominated by matter, right? That started around 47,000 years after the Big Bang process started. 40,000 years and runs till about 9.8 billion years. So but in this cosmic dark age, started around 370,000 years after, and lasted somewhere in the 100 million-ish, 150 million-ish, and we're not quite sure yet. It's one of the things that the James Webb Telescope is investigating. The redshift goes from 1100 to 20. Temperatures go from about 4,000 Kelvin to around 60 Kelvin. So it goes from being excruciatingly hot to downright frigid.
60 Kelvin is like far below freezing. Like it's colder than any place on Earth.
Yes. So the coldest I've ever been at near the South Pole was 210 Kelvin. 60 is downright uncomfortable. And understand that one of the things that happens during this dark age is it is possible for liquid water to form.
Hold on. I have to flex for a moment. You guys think that 60 Kelvin is cold? Man, you guys gotta come hang out at an ultra
maybe
cold.
not.
You gotta come hang out with an ultra cold atomic physicist, and I can.
Yeah, but you got to put some skin in the game, right?
Yeah.
What skin do you have at microkelvin, right? I'm not.
That's true. That's true. But I can show you a nice glowing ball of atoms that are chilling.
I can pour you a cup of cold drink that is far lower than 60 Kelvin, my friend.
Yeah. So back to say so again around this time the density waves begin imprinting polarization signals on there. So even though the photons are going around, there's some polarization signals being imprinted on it. Another thing that happens is that because we've gone temperatures from around 4,000 Kelvin down to 60 Kelvin, there is a period of time where the universe was, let's say, between 373 and 273 Kelvin, which is what? You can actually get water molecules forming at this stage.
If you have oxygen.
If you had oxygen, right? But you don't, because we lack something. There's nothing glowing at this stage. So if there was, but again, we don't think there's any oxygen forming because we don't think stars have turned on yet. In fact, the definition of the dark ages is before stars form.
Yeah. And I was going to say, this is an area where I think we actually start to know a lot less, in a certain sense, than maybe we did about what we've mostly talked about in this episode. Yes. At least in terms of like relative to what you might expect us to know.
Yes.
Because Like here, the universe is turning into an environment that it's a dilute neutral gas at this point, but we don't exactly how those first stars formed is still very much
Yeah.
the details of that are not clear.
Yeah. And so when we start when we start H3, before 3, we're talking about stars, galaxies, and large scale structures. We're going to be talking about some of this thing about when did the dark age of the universe end and how did it end, and stuff. But understand that speckled thing that you saw with Planck, WMAP, Kobe, that is the beginning of the structures of the early universe. We begin to see in that the structures there, and we'll talk a bit more about how they're going to form stuff, because in BE3 we're going to talk about these structures, and then in BE4 we're going to talk about how those structures form planetary systems. Because remember, it's before Earth. We got to get to Earth, so stay tuned.
Like one thing to mention perhaps is like in the notes that I have here is that at this stage in the cosmic dark ages you have 2 sources of photons, the CMB and also the 21 centimeter radio waves by neutral hydrogen, and that will be very important when we discuss the next stage when the first stars appeared.
Yes. So I think we've come to the end of the of this era in the universe. We've left the universe in the dark, and we've left you in the dark, quite literally. And we will see what happens in BE3.
Does anybody in the chat have any questions for us before we do our sign-offs or anything?
And talk about what's coming
Speak
up.
now or forever hold your peace.
Any questions? Any comments? Chat. You know, as they're saying, it's that the Big Bang Flash is certainly quite a triumph, and I congratulate those people involved in that process. Nowadays, microwaves is kind of pretty much commonplace. I mean, you probably have a microwave transmitter in your kitchen, but back then it was pretty big tech.
Yeah, it's once you get higher frequency than microwaves that it starts to get really difficult.
Yeah.
Like millimeter waves, that's a sort of a black hole of technology.
Yes.
It's very hard until you get up back into like the mid IR, basically.
If you're watching this live, if you could, or even afterwards, if you happen to like what you're seeing and click that like button, that thumbs up button, it helps this channel.
I'd say go subscribe to these guys too. I don't think they actually have official channels.
And we have I have a Discord channel that I can put an invite out. That Discord channel holds lots of stuff about science news and cooking and medical stuff and news stuff.
While we're waiting for any questions to come up, you guys want to plug anything coming up on your that you're going to be on?
I will be tomorrow. I will be having another episode of Bad Science Sunday, and that I think we might be doing Roger again. I'm not sure. But
Mr. Rogers?
No, the Mud Fossil dude.
Oh,
but yeah.
Excellent. Others?
Well, I'm mainly on Jackson Wheat's channel, so if you want to check out this channel, then I'm okay. Yeah.
Well, coming up April 4th, 2024, for those that are in North America, we have a total solar eclipse where the moon covers the sun. The path goes through Mexico, through Texas, and on up into the coast. It is a pretty good time. The moon will cover the sun around 4 minutes plus. And the nice thing about total solar eclipse is that when the moon completely covers the sun for those 4 minutes plus, you can look directly at it without filters, telescopes, and you see the corona as it is. It
But be
is
careful.
probably one of them. No,
It's
you don't
the
have to be
most
careful.
amazing thing I've ever
You
seen.
can look at it directly, right? There's no problem with looking at total solar eclipse directly.
Yeah, but
And,
you have to be careful minding the time, because at one point the moon
it's
will.
really obvious when
Yeah,
the
the-
sun
Yeah.
rises and
Yeah,
sets. It is, in fact, it is probably one of the most dramatic things you will probably see in your life. If you've never seen a total solar eclipse, it's dead obvious when it starts and when it stops.
It is probably, I can't think of anything else that I would put higher than it as the most amazing single thing I've ever seen with my eyes. I was able to see it in Wyoming in 2017.
I
and
was near the Tetons myself.
Yeah, it was.
Yeah.
It was totally worth the 6-hour drive and everything that I did to do it. I wish I could afford to get on a plane and go to somewhere where it was going to be. But I'm going to miss this one. But it's worth a trip, people.
And even the diamond ring, where we have a second or two of the sun setting or rising, you're not going to destroy your eyes.
But be careful. But be careful, guys. I something that I was watching it. I totally blocked time and missed my doctor appointment. So I've
seen 18 total solar eclipses. I have almost 50 minutes of totality now in my belt. And each total solar eclipse is different. So what you saw in 2017 was spectacular, but the sun is a very dynamic thing, and it's doing stuff. Now the sun is at this solar maximum where it's got all kinds of sunspots and flares. There's a comet up also that we might be able to see, although I wouldn't waste time looking at comet because you can see.
You're gonna make me buy a plane ticket. Don't do this. Stop talking.
And the other thing is to see the helium flash. So I have a thing where I go between just straight and I got a polarizer to see how the polarizer, because the magnetic field of the sun causes the corona to shift, and so you have two polarizing things. You can see back and forth. You can see the sun going boop, 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 because of all the stuff. And then when you put the gray spectrum, you can see the helium flash, right? Because you're seeing now in the chromosphere, very high temperature. You also see other higher energy state material in the corona. The spectrum, you can actually see that happen. In fact, the first detection of helium. The reason why helium is called helium is because they noticed the sun had this weird glowy stuff that chemists had never detected before, and they called it helium after the Greek thing after the sun. That's why helium is called helium. And in fact, you can see that when the corona is there, you can see this. It really is a strong the onset of the spectrum shift is quite dramatic. To boom, right? And then and if there's eruptions, you can actually see in real time stuff coming up behind the sun, coming up, launching in space, and coming back down, and so forth. It is worth it.
We only have one question. It's what do y'all think of I can't pronounce it.
Apophos, I guess.
I think it's referring to the asteroid Apophis. That is like probably a media hype. Like it's just like some people predict it will smash into Earth, but probably not.
I wasn't even aware of this.
and it has about it's an object that's probably I think the diameter is around 370 meters, something like that order, if I recall correctly. And it has only about a 2.7% chance of hitting the Earth. So it's another way to think about that is it has a 97.3% chance of missing. It's pretty good. It's pretty likely to miss. But in April 13th, 2029 is its close approach. It may be something that is close enough
it won't hit us.
You'll be able to see. You might be able to see it as a disc rather than just a dot.
So no Yucatan rerun.
Yeah, no. They did follow up that like observations that constrained the orbit more, and it should miss us. The initial paper, I guess, was like 2.7% chance, which is concerning.
Yeah,
but
I know it's now around. Actually, right. It's probably now they've got a much better refined thing.
Now it's I think negligible, basically.
Okay, I stand corrected on that. Yeah, that's right. It was the initial thing. I was thinking about the initial.
Yeah.
So back to say, so the eclipse is happening. There are a couple of other items in there. We have another on April 12th on Cheshire Channel Debate Hub at 1 p.m. Pacific. We're going to do another update on the Kilauea volcano and whether it's erupting or not. We have predictions that it won't be erupting, but Madame Pele does her own thing. So that'll be the case. And there's also, we have a Before Earth show on April 20th, BE3, where the Dark Ages will end and stuff will happen. Stay tuned for what that is definitely like.
Yeah, the Hollywood episode, because we're finally getting to see the stars.
Yes, excellent. And there's also Unnamed Tavern on March 30th. The thing with Dapper and Chesh and Monty and myself talk about things political. That'll be on March 30th at 15:30, 3:30 p.m. Pacific on Cheshire Channel.
If you want to say your catchphrases, your closing catchphrases, say them now if you have any.
I don't have any.
I hope you have a wonderful time, and I hope you continue to enjoy our favorite universe.
All right. Never stop learning and enjoy the randomness. We'll see you in a month.
Bye.
Bye.